everybody, and welcome to our second class on ggplot. And today we're going to reuse and expand our ggplot skills to apply it to our custom ChIPseq data and plot just a couple results. So we're going to kind of distill it down now into using our own data, reapplying some of them, and some tweaks we can do towards our goals. And so I'm here on class 2023 classes. We are now in 05R analyses, plotting, and plotting 2. This is the code I'll be using in my R Studio. And if you are on the web taking it in the class from here, we are finishing up our ChIPseq analyses, and we'll move on to metaplot soon. And look at our data in a sort of average, like how do our peaks look? Okay, so we're moving along quite well here, and we are going to do plotting 2 and go from there. Okay, so I'm here with that same markdown, and environment is empty. So we're going to load our plotting functions and our setup themes that we had from the previous class and in your util. I'm just going to load everything we need here. Okay, and so now the first thing we need is data. And so we are going to load our environment from 01 peak features, where we created a bunch of things like lncRNA promoters, mRNA promoters, genes, and all kinds of things. And so now we can just quickly load this, and we see all of these objects are now in our environment, and the one we're going to be sort of focusing on is this numpeaks df, where we have your DNA binding proteins here, peaks, and a bunch of data about peak overlaps, and we're going to use that to plot. Okay, so we now have that in our environment, and we will start with just a simple histogram of the number of peaks in our consensus peaks. So we will put in numpeaks df and say the x-axis is just the number of peaks. These are the peaks that overlapped in all the replicates, or our consensus peaks. And then we'll use a geom histogram with 10 bins, because I only have 7 proteins in there. And we can see here that 3 of my samples are 10,000 or less, and so they range up to 40,000 peaks in the samples. And I can go look at that in numpeaks df here by just simply looking in numpeaks at the values. Okay, so that is just starting slow, which is basic ggplot, setting the geom as a histogram, so we don't need a y-axis, the aesthetic layer of what column in the data frame you want to use, and we use numpeaks. Okay, so now we're going to plot what we've been plotting is the number of peaks versus the total amount of DNA that's covered. And so here we're going to make a point plot. We can forget these labels for now, they're just titles. Set the aesthetic layer where the x-axis is the number of peaks and y is the total peak length covered by those. So the sum of the width of the peaks. And we'll do a point plot, and we can just run that here without adding the labels. And we see what we saw in the previous class with the bigger data set, sort of a linear trend of the more peaks you have, the more DNA you cover. Kind of makes sense. And we could run this whole thing and get titles on there. So what we're doing, we have an analysis result. And so it's good to go to your working directory here. I'm in plotting and made a folder called figures. And now we can use this function ggsave here to save. All it needs is the file path, and I'm putting it in this figures folder, and you can save it there. Okay, so that's nice. We have our first figure that our DNA binding proteins, the more peaks they have, the more DNA they cover. And so now we're going to compare how many overlap promoters. And so we have that value in our numpeaks df because we did the overlaps with promoters in 01 peak features. And so what we're setting here is we're saying here's the data frame, num peaks df. The x-axis is the number of peaks, and y is the peaks overlapping promoters column in num peaks df. And I believe it's all the way at the end here, peaks overlapping gene bodies, peaks overlapping promoters there. Okay, so that's what we're plotting. And now what we'll take a quick look at what that looks like. And that's the same, basically the same kind of trend. It's different data. Basically, we're saying the number of peaks pretty much correlates with the number of promoters that are overlapped. This one might be an outlier and doesn't like promoters. So we could say the null hypothesis would be a 45-degree angle or a slope of 1 across this plot where as you get more peaks, you get more DNA coverage. And so we can add a geom ab line where we establish what the slope is, and we're going to say 1 and make it a dashed line as a second parameter separated by the comma. Add also a geom smooth, which is going to take the average of the data using a linear regression model. You can use other methods in geom smooth, but this is a handy thing we'll use all the time. And we're not going to show the standard error. It's pretty bad because we have very few dots. The formula is y to x, that this would be a 45-degree angle, like we are putting in here. And then this is from ggplot to plot the R value of the slope and the P value and the X limbs and Y limbs. So we're getting here pretty good at adding different layers. And we'll go through this again here because it's a lot, but it's nice that we can customize it so much. So we just made that, and now we'll add this dashed line. This was what would expected if the number of peaks directly correlated with the number of promoters overlapping, and some of the data fits that. Some of it is has more peaks than would be expected to be here. Okay, so that's nice. Now we can add this trend line with geom smooth here, and we can see we get this kind of thing here. If we added the standard error as true here, it would look I believe quite a lot of error. Yeah, we can see the gray is the error, and so that might be something you want to include to show how much variance there actually is in your data. Then we can add this stat line equation, which gives you the actual values that you're looking for here. I missed the parenthesis. Here, where we get the value of the line as well. Then we can set the x-axis and y-axis limits there with xlim, just adding layers, run that, and we can see it's just a little cleaner, and we see sort of a flat line. Some data follows the trend and some doesn't seem to. And then we can add the labels, and we have a nice figure here of our analysis, and we're sort of good to go in showing the relationship of the number of peaks and how many promoters are overlapped, and that you see that around 10,000 peaks, most of the promoters are covered, and you don't gain more promoters as you gain more peaks. Okay, and then you can use just ggsave in the file path and save it. And we can do the same thing for peaks overlapping gene body or any column. You can basically copy and paste the same code and then just change the column that you want to plot. So we're going to compare now the number of peaks to those overlapping gene bodies and see how this changes. So really just doing the same thing here. Data frame num peaks df, number of peaks versus peaks overlapping gene bodies and a geom point. And let's see what we look at there. Oh, interesting. That does look more linear. Okay, so maybe gene bodies are telling us more information that explain the relationship between number of peaks in a linear way to those overlapping gene bodies. Okay, so then we can add the ab line and the smoothed line that we did before, and sort of move along the same code as up above here. And we see, oh, interesting. Yeah, that is much more linear than the previous one. And we can add the equation for that here with that stat line regular equation. But here we're just adding where to put it on the position in the graph, so it doesn't overlap. And then the X limbs and the labels. And now we've just run essentially the exact same code up to here, and then changed the limits and added different labels. And we get this beautiful figure here where we see the slope is almost 1.67. That's pretty good. And it's kind of on a linear slope. So if we look at how our ChIPseq data is lining up, it's overlapping gene bodies quite a bit more in a linear way than it is with promoters. So we have some results already, and then we can save that and start collecting our results. And so now we're going to move on to looking at how many binding proteins events there are on promoters. And we made that in peak features using our count peaks per feature function, and essentially have a matrix of rows being promoters, all the promoters, and then the columns being your DBP of interest. And if there's an overlap, then there's a 1 or a 0 if there's overlap or not. And we'll get into that more in a second, but let's load that in. It's in our O1. We made this in O1 peak features, and just going to read in peak occurrence DF. It's much faster. So we can see we have, I apologize right now, peak occurrence is in the rows are promoters and the columns are your DBP, and a 1 or 0 if it overlaps that promoter. Okay. So now we can do a density plot and see where the density of the number of DBPs that bind in these regions. So, okay, so we're going to give it peak occurrence DF and see what's the density of genes that overlap promoters, and how many promoters are binding how many proteins, et cetera, is kind of what we're trying to do here. And so let's just look here at our aesthetic layer. We're adding X is the number of DBPs. And so we're going to have the number of DBPs across the X-axis, and then we're going to make a density plot with genome density here, change the alpha, the shading that we've gone over before, and manually set the colors. And so let's take a look at that. Okay, so what we see is most of the promoters have 0 DBPs on there. So this is the number of DBPs on a promoter. And we can see most are at 0. A small portion have 1. Some promoters have 2, and some have up to 5, but I have 7 possibilities, and it doesn't look like that happened. So with the 7 proteins I chose, they don't bind to most promoters, which probably makes sense, and that a given promoter will only see 5 of the 7 proteins in my samples, and we'll get into which ones they are, et cetera, in further analyses. So that's kind of a nice thing about promoter peak occurrence, is we can get a bunch more data of the number of promoters that have a certain amount of events. And this is just adding labels here. So making this have more information for it to save. So we can see where there were thinking more about peak occurrence. It's a really useful thing to have. And we can think about it some more here by filtering and using it to say, where are the promoters that have no binding events with my DNA binding proteins? Or if we did greater than 1, meaning where the promoters that have at least 1 amine, greater than 2, at least greater than 2. So you can just flip that if you want. And we're piping the peak occurrence data frame. Again, we have the rows here as promoters and the columns as whether a 1 or 0 if it occurred or not. And then we will filter this to any one that had less than 1 binding event. Okay. So we can see how many there are. Okay, wow, 18,000. This is from the big data set. And so I have 18,000 unbound out of 36,000 promoters. Okay, so about half bind my things. I could save that as a starting point here. Just information you might want to keep along the way, and how to think about keeping your code in line with things you might want to keep as results down the road. Okay, so here what we can do is plot compare long non-coding RNA promoters to mRNA promoters. And this is really an exercise in the aesthetics layer as how we can add multiple layers or multiple lines onto the same figure. This way, we'll do it another way that's a bit simpler in just a minute. So what we're doing here is saying numpeaks df is the data frame that we're going to put into memory. And so the x-axis is going to be number of peaks. But then we can add multiple y-axes here. And so we have a geom point with, now we're calling up the aesthetic layer again. So we're just saying, here's one aesthetic layer, add another one, add another one. Okay, so with geom point, the y-axis here is peaks overlapping lncRNA promoters, color them red, okay? And those overlapping mRNA promoters in the mRNA's promoter, color them black. So we'll have the number of peaks and then the number of overlaps for mRNAs and the number of overlaps for long non-coding RNAs, all in the same line here. And so we can see that's the case. And it looks like our mRNA, the black dots here, are more, have more overlaps with lncRNA promoters with promoters and the number of peaks, because this is both sets of promoters. Okay, and then we can add a stat line here to put out the equations for them. We can do that here. So we can get the slope is only 0.047 and 0.067, so it's not that great, but we can see that the intercept is 3,900, and so it's 4 times bigger than the long non-coding RNA one. So we could start to conclude from this already that mRNA's promoters had more binding events with my proteins than long non-coding RNA proteins. And so then you can save this, you can add these other regressions if you want. And then, so that's one way of doing it, is where we can add multiple aesthetic layers. So that's kind of a nice thing. We learned how to do this once, we can just add more of them. And you can keep adding lines as you please. And so another way of doing this is to sort of color by in the aesthetic layer. So we can do this in much less code by modifying our data frame to have information for us about what type is it, long non-coding or mRNA, and then whether there was an overlap or not, and then plot that. So we did that with code in a previous class, and now we're kind of doing it again and in a different way. So the way we can do that here is actually what we're doing is just removing this column from our numpeaks data frame by running this code here. So we can see now if we run this, we no longer have in our numpeaks DFL the one overlapping just promoters. We have just lncRNA and mRNA separated now. Okay, so that was the first step. And now pivot longer, we're going to do more of, but this is a great example of it. So if we look at numpeaks DFL right now, there's 7 rows. And if we pivot longer, what we're saying is, give me the information in rows from these columns as new rows. And so the columns we're going to do is take peaks overlapping lncRNA promoters and peaks overlapping mRNA promoters. We're going to take those two columns and make them each a row. So we're going to double the number of rows, and we're going to take the names too. So the parameters here is the column names needs to be in pivot longer, the names too. And we're going to do that in gene type, where we have whether they are long non-coding RNA or mRNA. Rather, we are going to make that column called gene type a new column, and the values will be peaks overlapping promoters. That will tell us the values from the lncRNA or the mRNA promoters separately. So if we see this here, now we're going to run the whole thing to here and look at our num-peaks DFL. We can see now there's two entries for each one, and that's because there was the entry for the long non-coding RNA promoters and the mRNA promoters, and we made this new column gene type. So peaks overlapping mRNA promoters or peaks overlapping lncRNA promoters is what we just made here with the values. 2 is saying peak overlapping promoters, and then this one substituting that for that in the gene type. Okay, so here we haven't done that mutate yet. So we're gonna run this again and just take a look at where we are with it. And we can see that each one has 2 entries. And for each entry here, we have a lncRNA mRNA thing that we can separate by. So now we can color by this gene type, so to speak, because we pivoted longer and gave each DNA binding protein an entry for the 2 different categories. And we'll do that more later, but I just think it's a great way to play with this posit and run this through step by step and see how it changes. And then now we're going to take the gene type where it says peaks overlapping whatever lncRNA or mRNA peak overlapping. So we're going to take this string and substitute it for nothing. And then we're going to do that in the gene type column, which is here. Okay, so then if we now run that mutate, we're going to get just the mRNA or long non-coding RNA promoter term in num-peaks DFL, which we can now see lncRNA promoters, mRNA promoters, just cleaning it up. And now we in ggplot can plot different plots here rather than typing the code for them in the different aesthetic layers. And so now we're ready to plot this. So we have our num-peaks DFL where we can take the number of peaks, and then Y is peaks overlapping promoters, and the column that we're going to color by now is gene type and make it point. And we can see we get that same plot that we had before. Last time we set the colors to black and red. These are just default ggplot colors. And we can see again that mRNAs, the more peaks they have, the more they overlap promoters, whereas lncRNAs kind of go flat here. Okay, and then we can add in the smooth line and then the labels the same as before, so I won't go over that. So that's it for now. And you can go ahead and go back. There's an exercise here to just pick some columns in the data frame and make a plot of them, or facet by a few different other columns. I think facet is a great thing to learn. And then also how you can pivot wider, make a new category that you can color by in ggplot. And so that's the sort of figures we wanted to make for our data. And now we're going to continue on with clustering and metaplots and other ways of looking at our data, heat maps of where the proteins are bound. And so lots more to explore, but we have some basic ggplot skills here now and some figures on our custom chip set. So thank you, and be well.